For the spectrometric analysis of a mixture experiment, you're going to use UV-vis spectroscopy to measure the concentration of two components in a mixture. And those two components are irioglycine, which is blue number 1, and tartrazine, which is yellow 5. Okay. These two components, these two substances are common food dyes. You'll see them all the time in various beverages and things like Jell-O and anything that has a color, candy. You're going to see these two components a lot. So we're going to measure the concentration of irioglycine and tartrazine in a mixture that I've prepared, so we know the concentration of these. Well, at least I do. You're going to determine that using this method. And also in a couple of sports beverages like Gatorade or Powerade. Maybe Kool-Aid. So in any case, how are we going to do this? So we're going to, like I said, we're going to use UV-vis spectroscopy. And so that means we're going to measure the absorbance of a mixture, or absorbance of these mixtures, and we're going to collect a spectrum. And so on our x-axis we're going to have wavelength, which we sometimes abbreviate as lambda, and that's going to be in nanometers. So we're going to collect absorption spectra, and from there we're going to get a few data points of interest. The absorption maximum at a particular wavelength, for a number of different wavelengths, 2 different wavelengths, to determine the concentration of these two species. So we know Beer's law, where the absorption is equal to the molar absorptivity times the path length times the concentration. Now this is true for one component. So if you have a pure substance, we just put blue number 1 in solution, we measure its absorbance. The absorbance is going to be proportional to the concentration and related to that via the molar absorptivity. But if we have a mixture, we're going to have 2 components contributing to the absorption. And so for a mixture, we're going to have the molar absorptivity of component 1 at some wavelength x times the path length times the concentration of that component, plus the molar absorptivity of component 2 at that wavelength times the path length times the concentration of that second component. So the the absorption is equal to the sum of its components, sum of the absorbances. Okay, again, B is the path length. And for our experiments, this is we're going to be using a 1 centimeter cuvette. So the path length is going to be equal to 1 centimeter. Now, we don't know the molar absorptivities of the 2 components at these particular wavelengths. So this is something we're going to have to determine. And that's actually quite easy to do. We can use Beer's law to determine that. But I want to look at the units here quickly. Let's just look at Beer's law. Okay, for a single component. The units on absorption are unitless. And typically we see molar absorptivity units as liters per mole centimeter. And our path length is going to be in centimeters. And our concentration is going to be in moles per liter. And so you can see centimeters cancel, liters cancel, moles cancel. We end up with a unitless value, and that's what we want. So we know that the absorbance is going to be the sum of the individual absorbances of the components in a mixture. So how does that look spectroscopically? So let's say we have a component with an absorption spectrum that looks like this, and a second component that has an absorption spectrum that looks like this. Typically, when we are determining the concentration of a substance based on its absorbance, we're using the maximum of that absorbance. So for this first component, that's going to be here, and for the second component, that's going to be here. Now you'll see in this figure that the second component absorbs pretty strongly at the absorption maximum of the first component. And the first component still absorbs at the maximum of the second component, but it's just not as strong. However, it will have an effect on the total absorption of the mixture. So if these are our individual components, the absorption of a mixture, I'm going to offset it just a little bit, will look something like that. We'll have two peaks based on where the peaks are for the individual components in that mixture. So as I said, we need to determine the concentration of a mixture based on the molar absorptivities of the individual components. And unfortunately in this equation we have two unknowns for a mixture. We don't know the concentrations. Okay, we don't know what C1 is, we don't know what C2 is. So what can we do? What this equation is saying is that the absorbance at a particular wavelength x is equal to the sum of these two components. So if we measured the absorbance at a second wavelength y, we would have a second equation but the absorption of the mixture at a second wavelength is equal to the molar absorptivity for component 1 at that wavelength times the path length times the concentration plus the molar absorptivity of component 2 at that wavelength times the path length times the concentration of component 2. Now we have two equations and two unknowns, so we can use algebra to solve our problem. So what we need to do then is determine molar absorptivity 1 at wavelength x, molar absorptivity of component 2 at wavelength x, molar absorptivity of component 1 at wavelength y, and molar absorptivity of component 2 at wavelength y. Now we can do this if we have solutions of the individual components of that mixture, which we will. And so what you're going to do is measure the absorbance for one of the components, or each of the components, with different concentrations. Okay, so you'll collect spectra. You're going to pick out that wavelength of maximum absorbance. You're going to write down what these absorbances are, and then you're going to plot that versus concentration. And so you're going to get something that should be linear. And why should that be linear? It's because it's based on Beer's law. The concentration is proportional to the absorbance. And Beer's law is written in the form of y equals mx plus b, where our intercept b is 0. So our slope is equal to the molar absorptivity times the path length. And we know that the path length is equal to 1 centimeter. So our slope is essentially equal to the molar absorptivity. So if we measure the absorbance at a particular wavelength x for component 1, we'll get the molar absorptivity of component 1 at wavelength x. If we do this at component y for component 1, or at wavelength y for component 1, we'll get u1's y, and so on. So what you'll need to do is come up with 4 calibration curves for your individual components for area-glossine and tartrazine at 2 different wavelengths. So you have 4 calibration curves. Area-glossine at wavelength 1, area-glossine at wavelength 2, tartrazine at wavelength 1, tartrazine at wavelength 2. And you'll get 4 different molar absorptivity values. So after doing that, you'll be able to plug in these 4 values, these 4 values, and you're left with not knowing C1 and C2. You're going to know the absorption of the mixture. We're going to measure this at these 2 wavelengths. And so you can rearrange your equations and solve for C1 and C2. A couple other things to note. Okay. How to use the instrument will be explained by your TA, but there will also be a brief document at the instrument to help you get started. And when you're measuring the absorbance of the mixtures, please do that in triplicate, so measure it 3 times. That way you can get statistics at the end for comparison of the different solutions that you're going to measure. But I think that's it. This is there's a lot going on here, but once you get started in the lab, I think you'll find that this is actually pretty straightforward. And you should see this topic come up in lecture as well.